All right, so far we've looked at 3 different methods to solve a system, and we've always got a solution. Whether we solve graphically or using substitution or elimination, we get some sort of solution to our system, right? So graphically, let's think about that. What does it look like if we get a solution graphically? What would you look for on the graph? Yeah. The intersection point, exactly, right? And then algebraically, that usually looks a little, you're not going to see an intersection point, but you'll be able to solve for one variable by essentially reducing the equation down to one variable, right? So, and then you can use that to get the other variable, right? There's actually more possibilities, though, than only having one solution, and that's what we're going to talk about today, okay? So the possibilities, it's very likely that you will get one solution. So that's the first possibility. And graphically, what will happen is you will see an intersection. Oh man, why does it do that? You will see an intersection point of the 2 lines. Okay, so that's what happens when we get one solution. And most of the time, this is what happens. Okay, but there actually are other possibilities as well. Okay, so if graphically you have to have an intersection point to have a solution, would it ever be possible to not have any intersection point? And if yes, what would that look like? So the solution is 2 lines that intersect. What would it look like if the lines didn't intersect? What would they be? Yeah, parallel, exactly. Yeah, so if we end up with parallel lines, we actually will have no solution because those lines never intersect. Right? So what would that look like? Oh, that doesn't look hold on. I gotta fix that. Okay, I'm gonna do this right head on. Okay, there we go. That's a little better. There's a set of parallel lines. Okay, and if your lines end up being parallel to one another, you will never have a solution. You'll never have an x, y value where in both equations, when you sub it in, you have equality. Okay? Now, there's actually a third possibility as well. Can anyone think about what that might be? The lines could either intersect or be parallel, or what else could happen? Yeah. Yeah, the lines could overlap. And if the lines overlap, then you actually have infinite solutions. Any point on that line would be a solution to the system. Okay, so this is the third possibility. And that is infinite solutions. Yes?
What if the lines intersect twice?
Okay, can you ever think of a situation where 2 lines intersect exactly twice? No, it's not possible. Yeah, so these are the only possibilities. What you could have, though, and you'll look at this next year, is you could have other types of systems where one of them is maybe a line and another one's a curve. And then you can get lots of different possibilities. So, for example, I'll just do this on another page, right? If you have other systems that are nonlinear, then let's say you have, this is a parabola. And I've talked about these before, that these will have something with an x squared in them. If you have a parabola and a line, Yeah, you could get two intersection points. Or you could have a parabola and another parabola, and also have two intersection points, right? Or you could have no intersection points, or they could overlap. So there's, as soon as you introduce different types of equations, this changes, right? But two lines will only ever intersect once or infinitely. Those are the only possibilities. The other thing I want to show you, because this is kind of, I think this is cool. We are going to learn in our next unit about trigonometry. So it sounds scary, but it's really not. It's just a way of figuring out side lengths of triangles and angles of triangles, basically, of right triangles. But in grade 12, you will look at trig functions, and those actually look like a wave. Like this. And they just go on forever. And if you have one of your functions a trig function, and the other function, let's say a horizontal line, you will also get infinite intersection points. Okay? But it's less infinite than if they overlap. So I love talking about how infinity can actually be different sizes. I think it's so fascinating and it blows my mind. But yeah, like this will have infinite intersection points, but it's almost more finite than if they overlapped, right? So yeah, there's lots of other possibilities as soon as you look at different types of functions or different types of systems. But for a linear system, it will never intersect twice. Okay. Now, what I want to talk about, though, is how do we tell? Like, we can see from the graph what's happening, but if we have an equation, how do we tell from the equation? What do we need to look for? And what I want to remind you of when we're thinking about this is that in slope-intercept form, all lines look like that. All linear functions, I should say, right? If it's a vertical line, then it won't look like that. But if we're just considering functions, they will take that format, y equals mx plus b. Which means that there are only two parameters that make one line different from another. And that's the value of m, the slope, and the value of b, which is the y-intercept. Okay? So when we're trying to come up with some criteria as to what situation we're in, I want you to consider those two parameters. Okay? If we're in this situation where we have one solution, how could we tell from the equations that those lines will intersect? Think about the slope and the y-intercept and what we would have to see. Might actually be easier to start with this one. Let's start with this one, with infinite solutions. What would you see with the slope and the y-intercept if the lines overlapped?
Same slope and same
Yeah. Yeah, they would be exactly the same equation in slope-intercept form. You'd have the same slope and the same y-intercept. They would be exactly the same. Okay? And these are called overlapping lines, or sometimes we call them congruent lines. You may have heard that word before when you look at congruent triangles. Congruent means exactly the same. Same size. For congruent triangles, it would be like same size, same shape, right? Okay, so that's the criteria for infinite solutions. What about if we have no solutions? What would you look for with the slope and the y-intercept? Yeah.
You have different y-intercepts but the same slope.
Yeah. If they're parallel, they have to have the same slope, right? But they have to have a different y-intercept because they need some space between them. If they have the same y-intercept, they'd be overlapping. So in this situation, these are parallel lines. We have to have the same slope, but a different y-intercept. Okay? And then what about if we have one solution? How could we tell from one solution? Yes?
Just different equations.
Okay, but like these ones would also be different equations if you had no solution, right? So what specifically would be looking for that's different?
Different slope and different line.
Okay, so different slope for sure. If lines have a different slope, they will intersect. What about the y-intercept?
I was just going to mention positive and negative slopes.
Okay, that's an interesting thought. Positive and negative slope. So yes, if one is positive and one is negative, they will absolutely intersect. But actually, they will also intersect if they're just different, right? So for example, if you have two positive slopes, one like this and one like that, they're both positive, but it still intersects at some point. Yeah. Okay, that's a good thought. Yeah, so definitely the slopes have to be different. What about the y-intercept? Yeah,
Doesn't really matter because they intersect on the y-intercept.
exactly. The y-intercept could be the same. If it's the same, it just means that's the point of intersection, right? So y-intercept really is irrelevant here. It could be the same or it could be different. Or different. I'm going to have to abbreviate there because I'm running out of space, right? So what that would, if it was the same y-intercept, then what you would see is this. Right, they intersect right on the y-intercept, okay? Yeah, but it really doesn't matter. For intersecting lines, all we need to consider is whether the slopes are different or not, okay? So what we're gonna do next is determine the number of solutions for these three systems, okay? Now, how do you think we can go about doing that? What would be a good strategy? Yeah. Yeah, convert to slope-intercept form, because ultimately what we're doing to figure this out is comparing the slopes and the y-intercepts. Well, we can do that best when they're in slope-intercept form. So we're going to do that first because usually that's what people do. They convert to slope-intercept form. But I do also want to show you at the end what it would look like algebraically if you have either no solutions or infinite solutions, because you can actually tell from that as well. Okay, so let's start by with A. I know I'm going to run out of space here, so I'll have to work downwards. If we convert these into slope-intercept form, for the first one, can you guys see we just have to subtract x from both sides? Yeah? So in slope-intercept form, this will be y equals negative x minus 2. Right? And for the second one, I could start by adding 2x. And so that would give me y equals, or sorry, negative 2y. I haven't isolated y yet. It's negative 2y equals 2x plus 4. And then to isolate y, I have to divide everything by negative 2. Okay, so that will give me y equals 2 over negative 2 is negative 1, so just negative x. And 4 over negative 2 is minus 2. Okay, so we're comparing this guy and this guy. What can we say about these lines? Yeah. They overlap, yeah. So if we're asked for the number of solutions, this would have infinite solutions. Okay, now for B, we've got 4x plus 6y equals negative 10. I think I'm going to do them sort of side by side. And negative 2x minus y equals negative 1. Okay, so to isolate y here, I have to start by subtracting 4x. And I get 6y equals negative 4x minus 10. And then I can divide everything by 6. And I get y equals, now what I would recommend doing is reducing these fractions for m and b, just because when you're comparing and they're not all reduced, sometimes you can miss the fact that they're equal or not equal. Okay, so it's not essential. You can also tell if you don't reduce, but I personally just think it's a good habit to get into. Okay, so there's my first equation. And then if I want to isolate y here, I have to start by adding 2x to both sides. And I get negative y equals 2x minus 1. Okay, have I isolated y yet? No, what do I need to do? Yeah, so you could multiply everything by negative 1, or you could divide everything by negative 1, right? Or you could just remember when you multiply or divide by negative 1, all the signs change. That works too. Okay, so here's one equation, here's the other equation. What can we say about the number of solutions? Yeah, one solution. How do you know?
It's different equation.
True, but you could have different equations that have no solutions. So what specifically are we looking for? Different slopes, yes. So different slopes. So one solution. Okay, and then for C, we have 3x plus y equals 1 and negative 6x minus 2y equals 12. Oh, thank you. Negative 1. Okay, so for the first one, I just have to subtract 3x, and then actually I'm done. Because this is already just y, right? So y equals negative 3x minus 1. And for the second equation, it's going to take a couple extra steps, but we've done this before. Start by adding 6x, and then we'll have negative 2y equals, that's a plus, sorry, it looks like a 16. 6x plus 12, and then I can divide everything by negative 2. Right, so we have y equals 6 over negative 2 is negative 3. Negative 3x, and then 12 over negative 2 is minus 6. So here's one equation, and here's the other equation. Okay, so what scenario are we in here? Yeah.
No solution.
No solution, yeah. And how can you tell?
The
Slopes are the same, and what else? Something else we're looking for, yeah. Yes, y-intercepts are different. Okay, so we have, in this case, no solution, right? These are parallel lines. Okay, now I do want to talk about what you would see if you tried to do this algebraically, because sometimes you trying to solve a system algebraically and you're like, what is going on here? I don't understand why I'm seeing what I'm seeing. And often when that happens, actually what's going on is you're in one of these two scenarios where you either have infinite solutions or no solutions. Okay, so let's actually, I'm not going to look at the second one because we've done a lot of examples where you have one solution and we know what that looks like. But I do want to look at algebraically, what would you see? Okay, so the infinite solution was the first one. And that was, what was it? It was x plus y equals -2. Was that one of them? I think so. And then the other one was -2x minus 2y equals 4. Okay, so let's suppose, I don't know, let's use elimination here because that's probably what I would go to first. How would you solve this by elimination? What would you have to start doing? Yeah. Yeah, multiply the top by -2 or by 2, right? If you multiply by -2, you would subtract. If you multiply by 2, you would add. Does that make sense? Okay, so you can do whatever. Yeah, we could do -2 by -2. Sure, why not? Okay, and then this, I'll just write this guy underneath, is going to become -2x minus 2y equals -2 times -2 is 4. Okay, and then to eliminate a variable, what do we have to do with these two equations? Yeah, subtract them, right? So when you subtract, you get -2 minus -2. Well, that's 0. Because it becomes -2 plus -2. Yes? You good?
Ms. Oppenheim?
Yes.
Can I ask you a question for a quick?
Yeah, just let me pause my recording.
Sorry. It's timely. How's everybody?
Okay, so tell me what you got. So -2x minus -2x is 0. What happened here? Yeah? 0 plus 0 equals 4 minus 4? 0. Okay. 0 plus 0 equals 0. Tell me about this equation. Is it valid? Is the left side equal to the right side? Yes. The left side equals to the right side always. Doesn't matter what x is, doesn't matter what y is. The left side always equals the right side. And this is what you will see when you have infinite solutions. You will get some sort of an equation that is always true that doesn't have an x and a y in it, right? This is always true. And doesn't involve x and y. Okay? If you use substitution, what you'll see is it won't be 0 equals 0. It'll probably be like 3 equals 3 or 10 equals 10 or something like that. But you will see the same sort of thing. A number equals a number, and they happen to be the same number. Okay? Now, if we do this with the situation where we have no solution, that was 3x plus y equals -1. Whoops, -1. And then the other one was -6x, right? What was this one? Plus 2y? Minus 2y, thank you. I should know that. And this was 12, right? Yeah? Okay, cool. All right, so if we were to solve this using elimination, how would you do that? Yeah. Yeah, we could multiply this one by either -2 or 2. I'm going to multiply it by 2 just because personally, I don't ever multiply by a negative number. And that's probably just habit. I just like kind of go with the flow, and if it happens to be addition, it's addition. If it happens to be subtraction, it's subtraction. But if you like to do that, that's totally fine. Okay, so this is going to become 6x plus 2y equals negative 2. Okay, and in this scenario, to eliminate, we would have to add because the signs are different. Yep.
So essentially for that, you're just trying to get them to have the same absolute value, right?
Excellent. Yeah, so you want the coefficients to have the same absolute value. Yes. Do you guys know what absolute value is? Yeah, does anyone not know what it is? Thank you for raising your hand. I bet you're not the only one. Absolute value is actually a distance from 0. So if you're looking at, let's say, I'm going to do this on the next page just so that it doesn't get messy. But let's say you have 0 here and 3 here. Okay, the absolute value of 3, we use these big 2 vertical lines to show that we're taking an absolute value. What is the distance between these 2 numbers? 3. If you take the absolute value of negative 3, what's the distance between these 2 numbers? 3, yeah, so it's also 3. Yeah, so absolute value is essentially just, in science, they often talk about the magnitude of a number, right? That's just like the number part where you don't pay attention to the sign. Yeah, exactly. So you want their absolute value or their magnitude to be the same. Yeah. Okay. Back to here. When we add negative 6x plus 6x is 0. Negative 2y plus 2y is 0. And 12 plus negative 2 is 10. Okay, so we end up with this equation that is 0 equals 10. Okay, so tell me about that. Yeah. It's not valid. It's never true. This is never, ever true. Doesn't matter what x is or y is. It's just never true. I like to use the word sometimes, it's nonsensical. It's like nonsense. Doesn't make sense. Okay? Yeah, so that is what you will see if you try and do this algebraically, either through elimination or through substitution. Again, with substitution, typically you don't see 0 as one of the numbers, but you'll have the same sort of thing. You might have like 2 equals 4, or 100 equals 1,000, something like that. Okay? Any questions with that? Yep.
Could you turn these equations graphic, like into slope-intercept form? Like, would you be able to still see that?
Yeah. Yep, so that's what we did here. Oh, I see what you mean. Like do substitution or elimination using the slope-intercept form?
So like instead of doing, I guess, substitution or elimination, you solve graphic.
Yes, yeah, exactly. And actually, so if you graph them, you would see it visually, but you can also see without graphing just by looking at slope-intercept form, right? Yes. Okay. So I'm going to skip this piece and move on, and then I'll let you guys come back to that at the end. We just have one more question to do, and then we're all done. Okay. Given the equation negative 2x plus y equals 4, write another equation that will form a linear system with exactly one solution with no solutions and with infinite solutions. Okay. So where would you start with this? Yeah. Yeah, I would convert this to slope-intercept form because the other equations are going to depend on what the slope and the y-intercept of this line is, right? So to convert this guy to y-intercept form, or sorry, slope-intercept form, we just need to add 2x to both sides. And we get y equals 2x plus 4. Okay. Now, if we want exactly one solution, what are sort of the restrictions on our equation? Yeah.
Different slope.
Yeah, different slope. So the only thing that we need to have is a slope other than 2. That's the only thing. M cannot be 2. Okay, so you could do y equals x plus 4. You could do y equals 1.99 plus x, rather, plus 5, right? Still different. These would look parallel, but in fact, at some point on the coordinate plane, they would intersect. You could do y equals -3/4 x plus 0, right? Those would all work. If you want no solutions, what are the restrictions?
Like the left side, the right side need to equal 0.
Think about in terms of the parameter of a line. Yeah. Okay, different y-intercepts. So B has to be, yeah, M has to be the same, 2. B can't be 4. Okay, so you could do y equals 2x. You could do y equals 2x plus 1,000,000. Those would all work, or anything in between. And what if you wanted to have infinite solutions? Yeah.
It has to be the exact same equation.
Right. So you would just either copy the equation. So M has to be 2 and B has to be 4. So you could do y equals 2x plus 4. But you could also multiply the whole thing by a number and write that down as well, right? Because when you convert it to slope-intercept form, you'd get the same thing. So let's say I multiplied the whole thing by 10. I would end up with 10y equals 20x plus 40. That kind of thing. All right? Any questions with that? Okay, that's it for today and for this unit.